Today we're going to look at undeniable signature schemes, and I guess this is sort of a variation on the basic signature problem. And so instead of just having setting up a system and having a protocol which could be verified by any user, the idea behind undeniable signatures is that Alice wants the signature only to be verified um, at a time of her choosing. So she can publish a signature, but it actually can't be verified without Alice's participation. Okay? And so that's done by means of a challenge and response protocol. Okay. However, if we're gonna use this paradigm, um, then there would be a potential for abuse by Alice, right? Because Alice could publish a bunch of signatures that may actually be valid, but then maybe refuse to confirm them at a later date. So what we need with these undeniable signature schemes is also a disavowal protocol. Okay, so whenever Alice wants to verify the signature one way or another, so verify that it's correct, or verify that it is incorrect, that it's a forgery, there'll be a protocol to go through. Okay, so there'll be a verification protocol and a disavowal protocol, and both of those will be in the form of challenge and response. Okay, so whoever's doing the verifying will issue a challenge to Alice, and Alice will have to respond correctly for various values of correctly in either instance, whether the signature is valid or not. All right, so we're going to look at an example of such a scheme. So this is called the Chalm van Antwerpen signature scheme, which we'll abbreviate as CVA from here forward. Okay, so Alice is going to set things up in the following way. So she's going to pick a Sophie Germain pair, so primes P and Q, such that P is equal to 2Q plus 1. So then an element alpha of order Q. Okay, so we saw a couple classes ago how to go about setting that up. An exponent A that's going to be between 1 and Q, and beta that's going to be equal to alpha to the A mod P. Okay. So as usual, A is log base alpha beta. And we'll do the usual thing here, which is so public parameters will be P alpha and beta, and A will be kept secret. All right, and so just a word on notation here. So remember that um, alpha with these angle brackets around it means the subgroup generated by alpha. And so we're going to be we're going to work in G, right, using the notation for a general group here. Okay, so G is going to be that subgroup generated by alpha, and just drop the mod notation again, just to kind of simplify our notation throughout. Okay, but since G is generated by alpha and alpha is of order Q, when we work in exponents, then all of the arithmetic will be done mod Q. Okay, so at the sort of the base level, arithmetic is done mod P, but at the exponent level, arithmetic is going to be done mod Q. All right. So how is excuse me? So how is the signature going to work here? So for a message X and G, so the signature is just going to be X to the A. Okay, so X comma Y is going to be the signed message. Okay, so before we continue, then just a word on notation. So we're going to be working in the subgroup generated by alpha, so we'll denote that by G. Note that the size of G then is Q. Okay. And so we're working at the base level, the arithmetic is still going to be done mod P, but when we're working in exponents, since everything is in the subgroup generated by alpha, that arithmetic will be done mod Q. Okay, so we're going to drop the mod notation to save a little bit of writing throughout, simplify our notation a little bit, but just be aware that we've got, as usual, two different moduli, one we're using in the exponent and one we're using at the base level. Okay. All right, so If we want to assign a message X, then so X should actually be an element of G, and then the signature will be Y, which will be X to the A, mod P. So then X comma Y is the signed message. All right, so for verification then, so Bob is going to choose exponents E1 and E2 at random. Okay, so again, those should be in Z mod Q. All right, so the challenge C then is going to be beta to the, so Y to the E1. So make sure I get the order correct here. So Y to the E1. Beta to the E2 for those choice of exponents. Okay, so Alice is going to compute D, okay, and so this is something Alice should be able to compute based only on the challenge, right, because Alice doesn't have access to these exponents. Okay, so D is simply going to be C to the A inverse, okay, and remember that, emphasis here, that inverse is taken mod Q. Okay. All right, and so then Bob's going to accept Y as valid if and only if what happens here. Okay, well, what should, or sorry, D is valid. So what should D be equal to here? Okay, so D is the challenge to the A inverse. Okay, but let's write the challenge in terms of X and alpha instead of in terms of Y and beta. So it's X to the AE1, alpha to the AE2. So that's all to the A inverse. Okay. And so that simplifies to X to the E1, alpha to the E2, and I distribute that A inverse. Okay, okay, so this is something that Bob can check. Right, because Bob does know these exponents. Okay, so Bob would check that D is correct. All right, so here's a little example. So I'm going to let the prime P be equal to 59. 2 turns out to be primitive mod 59, which we can check using Euler's criterion. So remember, when that's the case, then the primitive element's squared. It will be of order Q, so I can take alpha to be 2 squared, which is 4. Okay, so that has order 29. If I let A be 10, then beta is going to be alpha to the 10, which is congruent to 28 mod 59. Okay, so Alice wants to sign the message, which is 41, so she's going to publish X, and then the signature, which will be 41 raised to the A, which is 35. Okay, so the signed message is then 41, 35. Okay, then alpha inverse is going to be congruent to 3 mod Q, right? Because remember, Q is 29, right? So 3 and 10 are inverses of each other, mod 29. Okay, so now finally, time comes for the signature to be verified. Okay, so Bob's asking Alice to go through the verification protocol. And the choice of exponents are E1, E2, which will be 5, 9. Okay, so Bob's going to compute 35 to the 5 times 28 to the 9, okay, because this is Y and this is beta. Gets 21, sends 21 to Alice. So then Alice is going to compute 21 to the A inverse, so 21 cubed, which is 57, sends it back to Bob. Okay, and so then Bob's going to verify that by doing X to the E1, alpha to the E2, and checking that it does also reduce to 57 on P. Okay. All right, so far so good. But so there's a couple points that we need to address here before we even start talking about the disavowal protocol. And so one point here is so security against fraudulent signatures. Okay, so could anybody else come up with a forgery and fool Bob into accepting the forgery. Okay. Now, one thing to know right off the bat: the only way to produce the correct Y on a message X. So again, the only way to do a selective forgery is to know A, right? Because you've got to figure out what the value of right. If I want to figure out the correct signature on X, well, I have to raise it to the A, right, and reduce mod P, and this would then give me a unique value in that subgroup G. Okay, so the only way to do that is to actually know A. All right, so nobody is going to be able to actually produce the correct signed message pair, right, without breaking the discrete log problem. Okay, so that's great. But another issue may be that somebody could produce an incorrect signed message pair, right? So x comma y prime, where y prime is not actually x to the a, and maybe fool Bob into accepting the verification. Okay, so that'd be another way to potentially break the system. Okay, but the interesting thing here is we can actually show that not even Alice will be able to fool Bob into accepting a fraudulent signature. Okay, so if that second component, y prime, is not actually x to the a, then Alice won't be able to fool Bob into accepting the signature as correct. And since Alice won't be able to fool Bob, nobody else will be able to fool Bob either, because nobody else has as much information as Alice. Okay, so what we're actually going to show here is that Alice, and therefore nobody, can fool Alice, and they're confusing myself with double negatives here, but Alice can't fool Bob into accepting a fraudulent signature, and therefore nobody else can either. Okay. All right, so we'll have a theorem here, and so this says that if y is not the correct second component of the signature, so if y is actually not congruent to x to the a mod p, then any response given by Alice to Bob's challenge will be accepted by Bob with a probability at most 1 over q. And since q will be a massive prime number, that means it'll be accepted with a very small probability at best. Okay. All right, so let's see how we're going to prove this. Okay. All right, so first thing we're going to do is we're going to ask how many pairs of exponents, e1, e2, can produce a given challenge, C. Okay. All right, and so remember, C is ye1, beta e2. Okay. All right, the order of beta is q, right, because it's a non-identity element in a group of size q. So its order could only be 1 or q by Lagrange's theorem, but it's not 1, so it has to be q. All right, and there are q possible choices for each of these exponents. Okay, so there are q choices for e1. Okay. Once e1 is chosen, then e2 will be the unique log-based beta of c times y minus e1, right? Just moving the stuff to the other side of the equation. Okay. Remember, there's a unique value for that in z mod q. All right, so there's q possible choices for e1 that can produce the challenge. Once e1 is chosen, e2 is forced. Okay, so that means there's q total pairs. That could have produced this challenge. All right, and so what we're going to do then is we're going to show that So under this assumption, so that y is not congruent to x to the a mod p, we'll show that any response Alice can give verifies for only one pair, E1, E2. Okay, so since it verifies for only one pair, but there were q possible pairs that could have produced the challenge, then Alice is basically just guessing here, and there's only a 1 in q probability that she'll guess correctly. Okay. All right, so the way we'll do this then, so where alpha generates G. Okay, so on all these things are in G, so we can write everything here as a power of alpha. Okay, so I'm going to write C is alpha to the I. D is alpha to the J. What else do I need? X is alpha to the K, and then Y is alpha to the L. Okay, and so these things, I, J, K, and L, are all uniquely determined from the fact that the order of alpha is Q, so they're uniquely determined in Z mod Q. Okay. All right, and then we know it's, okay, so a couple of things here. So we assumed at the outset that Y was actually not the correct signature on X, so Y is not congruent to X to the K mod P. Okay, and then I can write that in terms of alpha. Okay, so alpha to the L is not congruent. I'm sorry, bring down. Well, yeah, okay, so let me write it in terms of exponents first, and then I can bring it down. Okay, so alpha to the L is not congruent to alpha to the K mod P. Okay. And then, again, bringing down the exponents, that implies that L is not congruent to AK, but mod Q, right, since the order of alpha is Q. All right, so now consider these congruences. Okay. So this is what we should have to verify. Right, so C was produced by Bob by doing y to the E1 beta to the E2 mod P. Okay. And then if the response actually verifies, what will we need? D is congruent to x to the E1 alpha to the E2 mod P. Okay, so this is what needs to be satisfied in order for Alice's response to verify. And so what I'm going to do then is, again, bring down exponents and write this in terms of mod the order of alpha, mod Q. Okay. Right, so so C is alpha to the I, so this becomes I. Y is alpha to the L, so this becomes LE1. Okay, beta is alpha to the A, right, so this becomes AE2. This is mod Q because I'm bringing down exponents. Okay, D is alpha to the J, so this becomes J. X is alpha to the K, so this becomes KE1. Right, and that's just alpha. Okay, so that just becomes E2. Okay, so again, the response verifies. These are really if and only if. So if and only if this system of congruences mod Q holds. But then this I can also write as a matrix equation for the unknown Z1, E2. Okay, so LA K1 times Z1, E2 congruent to IJ. Okay, so it's a matrix equation mod Q. All right, but now notice that the determinant of this matrix is L minus AK. Right? This matrix is invertible, right? If and only if its determinant is invertible mod Q. Okay, but notice we have here L is not congruent to AK mod Q. Right, so the determinant is non-zero mod Q, but Q is a prime, so the determinant is invertible. Okay, and so that means that the matrix is invertible. Okay, and so that means that this matrix equation has a unique solution for the unknowns E1 and E2. Okay. All right, so another way of saying that is in order to satisfy this system, right, there's a unique choice of E1 and E2, right, that will satisfy both of the congruences. Okay, and so that means that Alice's response D will only satisfy the system and therefore satisfy the second congruence, right, if Alice is picking the D that yields the E1 and E2 that Bob originally used. Okay. If Alice picked anything else, then the system of congruences, right, would hold only for a different E1, E2. Okay. But we also saw, right, that there were Q possible pairs that could have generated that C. Okay. So basically, again, so Alice is sort of guessing here. Okay. So verifies if and only if Alice picks the D, okay, such that the solution to that matrix equation is the original E1, E2 chosen by Bob. Okay. Otherwise, this is not going to verify. Okay. All right, and then so let's kind of summarize what we know here, right? So we know that so we've got the signature scheme, right? So we have Alice can sign messages. There's no way for right, for anyone to actually verify that it's Alice's correct signature without Alice participating in the protocol. If the signature is invalid, then Alice can't fool a verifier into accepting the signature. Okay? And therefore, nobody else can. So this is secure against forgeries of all types. Right? But now, so what's to prevent Alice from, right, publishing phony, or actually publishing correct signatures, and then verifying them if Alice chooses to do so. Right, so maybe Alice, signs a document agreeing to buy a stock at a certain price and at a future date. If the market price is actually higher, she verifies. But if it's lower, she refuses to verify or goes through the verification protocol and gives an incorrect value of D. So what we need then, in order for the scheme to be complete, is a disavowal protocol. So this is a protocol that Alice should go through if Alice is claiming that a signed message is a forgery. But the disavowal protocol should only succeed if that message is. So this is how the disavowal protocol is going to work. So essentially, we're going to run through the verification protocol twice. But in each step, Alice is going to give a response that doesn't actually satisfy the verification protocol, which should be pretty easy to do because most responses don't satisfy the verification protocol. But Alice has to complete this in such a way that the two responses are consistent with each other. Okay. All right, so just like in the verification protocol, Bob's going to choose a couple random exponents. He's going to compute the challenge, which will be y to the E1 beta to the E2. Mod P sends that back to Alice. Okay, and so Alice is just going to respond to this challenge in the same way that she would to the to a valid message in the verification protocol, which would be to do C, little c to the A inverse. Okay, as usual, inverses and the exponent are taken mod Q. Okay, then reduce that mod P, send it back to Bob. Okay, and so Bob's going to verify here that this doesn't actually verify. Okay, so that D is not actually congruent to x to the E1 alpha to the E2. Okay, all right. And then they just run through this whole protocol again, but with different choices of exponents. Okay, so with F1, F2 as the randomly chosen exponents. Okay, so big C is going to be so y to the F1 beta to the F2 mod P. So then big D is going to be big C to the A inverse. Again, so the inverse of the exponent is taken mod Q. Okay, nothing, reduce mod P. And then again, Bob's going to confirm that this is not actually what it would be if the signature was valid. All right, but then again, so what's if the signature was valid, what's to prevent Alice from calculating the correct response and then just changing it randomly? So what's preventing that is that there's a consistency check here. Okay, so Bob's going to check that little d alpha to the minus E2 to the F1 is congruent to big D alpha to the minus F2 to the E1 mod P. Okay, so let's see where this comes from. All right, so why are we checking this? All right, so the idea is then if the signature is invalid, okay, so that means that if we look at Z, I'm going to call Z y to the A inverse, and of course the inverse, assume for now on all inverses and the exponents are taken mod Q, okay, so that inverse is taken mod Q. Okay, so then the Z is not going to be equal to X. Right, because if the signature was valid, then y to the A inverse, right, would be sent back to X. The signature is invalid, so the Z is something different than X. However, it's consistent throughout the two parts of the protocol. So every time we're calculating y to the A inverse, then we're getting this Z. Okay. All right, so that's going to tell us then that so C, or sorry, D rather, okay, which is C to the A inverse, is y to the E1 beta to the E2, since this is C, to the A inverse. Okay. And if I rearrange this a little bit, well, the y to the A inverse, we've defined that to be Z. Okay, so this is Z to the E1, and then remember beta to the A inverse will be alpha, so it's Z to the E1, alpha to the E2. Okay. All right, and then similarly, I look at big D, which is big C to the A inverse. Okay, so I'm just replacing my E's with F's here. Okay, so that's going to give me Z to the F1 and alpha to the F2. All right, so I can take each of these congruences and essentially solve for a power of z. Okay, so I get z to the e1 is little d alpha to the minus e2. Okay. I get z to the f1 is big D times alpha to the minus f2. Okay, so Bob doesn't know z. However, whatever z is, right? So Bob knows that z to the e1 is this thing, and z to the f1 is this thing, right? So if we look at z to the e1 f1, I can obtain that in two ways. Right, so one by arranging the right-hand side of the top congruence to the f1, the other way by raising the bottom half, the right-hand side of the bottom congruence to the e1. Okay, so it's d alpha to the minus e2 to the f1, big D alpha to the minus f2 to the e1. Okay? And so notice that's exactly what we checked in this congruence here. So the idea then is if Alice's responses are consistent, so if Alice is actually raising those challenges to the A inverse power, then this z is consistent between those two responses. Okay? And so that'll be reflected in the fact that if we do d times alpha to the minus e2 and raise that to the f1, or do big D alpha to the minus f2 and raise that to the e2, that will actually be getting the same thing. Okay? All right, so the last thing to do is to prove then that if we have a valid sign message, okay, so we're going to be assuming in this theorem that xy is actually valid. Okay, so what we need to do then is prove that Alice cannot disavow, right? So similar to showing that Alice could not complete the verification protocol if we had an invalid sign message, we don't want Alice to be able to give a valid signature and then be able to disavow it later, right? Because again, Alice would be able to have it both ways then and would possibly be able to use that to her advantage. All right, so what we're going to do in this theorem then is we're going to suppose that xy is a valid sign message pair. Okay, so that means that y actually is x to the a mod p, and we're going to assume that they follow the disavowal protocol. So we're going to show then that if the two inconsistency checks actually hold, okay, so we have little d is not congruent to x to the e1 alpha to the e2, and big D is not congruent to x to the f1 alpha to the f2, then actually, right, the final consistency check is only going to hold with very low probability. Okay, so there will be only will be at most a 1 over q probability that the final consistency check holds, or another way of phrasing that, it will fail to hold with a probability of 1 minus 1 over q. Okay, but q is going to be a very large prime here, so 1 over 1 minus q will be very close to 1. Okay. All right, so how are we going to show this? Okay, so let's, for a moment then, so suppose that Alice is able to satisfy the consistency check. Okay, so suppose this last congruence is satisfied. Okay, so what we can do then is basically just a little bit of algebra to rewrite this. Okay, so if I raise both sides to the E1 inverse, and then bring the alpha to the f2 over to the other side, then I can solve this for d. Okay, so then d will be congruent to d naught to the f1, alpha to the f2 mod p, where d naught is just the stuff I would get by raising this to the E1 inverse. Okay, I'm not too concerned about the form of d naught. The point here then is that Alice needs to reply to this challenge. So y to the f1 beta to the f2 with this response d, that's of the form d naught to the f1 alpha to the f2, which means that Alice has to reply as if the signed message pair were d naught y, right? Because in this instance, right, so if the actual signed message was d naught, the response would be d naught to the f1 alpha to the f2. Okay. but the actual signed message wasn't D not Y, it was XY, right? And so we saw that Alice can only give a valid response, right, um, for that would work for a given signed message, right, with very low probability, right, unless that signed message was actually, right, the message that Bob received. Okay, so if Bob has a signed message XY, right, so the idea is that Alice won't be able um, to produce the response for a different signed message with that signature, right, unless those two original messages happen to be equal to each other. Okay. All right. So the idea then is that by the previous theorem, then Alice is only going to be able to give the correct reply as if the pair were D naught Y, um, with probability 1 over Q, right? So unless D naught to the A is actually congruent to Y mod P. But since X to the A is congruent to Y mod P, then this will actually only hold if D naught is X. Okay, so the question now is just, is D naught congruent to X mod P? Okay. All right, but by our first, our incongruence here, so D is not congruent to X to the E1, alpha to the E2. Okay. And again, I could just rearrange this and solve this for X. So this is saying X is not congruent to D to the E1 inverse, alpha to the minus E2 E1 inverse. Okay. But then this thing is precisely D naught. Okay, so that's just saying that in fact X is not congruent to D naught mod P. Okay, so that means D naught comma Y is not a valid signed message pair. Okay, and so remember, when we have an invalid signed message pair, Alice cannot produce the correct response, right, to that challenge, or at least would have to be incredibly lucky to do so, right? So she can only give the correct response with a very small probability, 1 over Q, but that's exactly what needs to be done for that final consistency check to be satisfied. So the upshot here then is that Alice is not going to be able to disavow a valid message, except with very low probability.